Deep in the vast expanse of space, there's a place where the rules of physics seem to bend and break. A cosmic playground of mysteries that even the brightest minds can't fully explain. Welcome to the COMA Cluster, a sprawling metropolis of galaxies where the ordinary becomes extraordinary and the unexplained becomes the norm. Picture this: galaxies moving in ways they shouldn't, dark matter vanishing without a trace, and ghostly lights flickering between the stars with no clear source. These aren't just anomalies, they're cosmic puzzles begging to be solved. In this video, we're diving headfirst into 25 of the most baffling phenomena lurking within the COMA cluster. From galaxies that defy gravity to black holes that play hide and seek, each mystery challenges everything we think we know about the universe. Some of these enigmas might even rewrite the textbooks. So buckle up, because by the end of this journey, you'll see the cosmos in a whole new light, and you might just question what's really out there, ready to uncover the secrets hidden in the heart of the COMA cluster. Let's begin. Now, let's zoom in on our first cosmic head-scratcher, a galaxy that's playing by its own rules. Meet NGC 1052 DF2, a peculiar resident of the COMA cluster that's throwing scientists for a loop. Here's the twist: this galaxy seems to be missing something crucial: dark matter. That's right, the invisible glue that holds most galaxies together is barely detectable here, if it's there at all. This isn't just a minor oddity, it's a full-blown cosmic rebellion. Dark matter is supposed to make up around 85% of a galaxy's mass, acting as the scaffolding for stars and gas. But NGC 1052 DF2 defies that expectation, with observations showing its stars moving at speeds that suggest almost no dark matter is pulling them. Imagine building a house without a foundation. That's how baffling this is. So, what's going on? One theory suggests this galaxy might have been stripped of its dark matter by a violent encounter with a neighboring galaxy, leaving it oddly bare. Others wonder if it formed in a rare, dark matter-poor environment, challenging our understanding of how galaxies are born. And then there's the unsettling possibility: what if our models of dark matter are missing a key piece of the puzzle? Whatever the answer, this cosmic outlier forces us to rethink the rules. Could there be more galaxies like this hiding in plain sight? And if so, what does that mean for our understanding of the universe's hidden architecture? One thing's for sure: NGC 1052 DF2 isn't just a curiosity. It's a clue, and it might just lead us to something even bigger. Now, let's dig deeper into the mystery of NGC 1052 DF2's missing dark matter. Scientists have proposed several theories, but each one comes with its own set of questions. First, there's the idea of tidal stripping, that this galaxy had a violent run-in with a larger neighbor, ripping away its dark matter like a cosmic thief. The problem: while tidal forces can strip gas and stars, dark matter is thought to be more resilient. So why would it vanish completely? Some simulations suggest extreme scenarios where dark matter gets flung out, but evidence for such an event remains elusive. Then there's the possibility that NGC 1052 DF2 formed differently from the start. Maybe it was born in a pocket of the universe where dark matter was scarce, like a tree growing in oddly nutrient-poor soil. If true, this would challenge our assumptions about how galaxies take shape, suggesting dark matter isn't always the invisible architect we thought it was. Of course, there's always the chance we're seeing an illusion, that observational errors or hidden factors are skewing our measurements. Perhaps the galaxy's stars are arranged in a way that mimics the motions of a dark matter-free system, or maybe there's unseen gas throwing off the calculations. But repeated observations keep pointing to the same puzzling result, making this explanation harder to swallow. The controversy around each theory shows just how much we still don't understand. If tidal stripping is to blame, why don't we see more galaxies like this? If it's a formation fluke, what does that mean for the rest of the cosmos? And if it's an observational glitch, why does the data hold up under scrutiny? NGC 1052 DF2 isn't just a cosmic oddity, it's a mirror reflecting the gaps in our knowledge. And until we solve its riddle, dark matter's role in the universe stays as mysterious as ever. Now, shifting our gaze to another cosmic enigma, let's unravel the mystery of ultra-diffuse galaxies, or UDG. These ghostly giants are as sprawling as our Milky Way, yet they contain only a fraction of its stars, making them some of the faintest and most elusive objects in the universe. Imagine a city the size of New York, but with only a handful of streetlights. That's the eerie emptiness of a UDG. The COMA cluster is teeming with these faint giants, and their presence there is especially puzzling. In such a dense, chaotic environment where galaxies constantly jostle and collide, you'd expect these delicate structures to be torn apart, yet they persist, defying the odds. Astronomers are left scratching their heads. How can something so fragile survive in a place so violent? One leading theory suggests that UDGs are packed with dark matter, acting as an invisible shield that holds them together against the cluster's gravitational onslaught. But here's the twist: some UDGs seem to have very little dark matter at all, adding another layer to the mystery. If dark matter isn't the answer, what keeps these galaxies intact? Could their stars be arranged in a way that makes them more resilient, or is there some unseen force at work? Then there's the question of how they formed in the first place. Did they start as normal galaxies that were stripped of gas and stars over time, leaving behind these faint skeletons, or were they born this way, emerging from pockets of the universe where star formation fizzled out before it could truly begin? Each possibility challenges our understanding of galaxy evolution, forcing us to rethink the rules of cosmic construction. The prevalence of UDGs in the COMA cluster makes them a key piece of the puzzle. By studying them, we're not just learning about these ghostly galaxies, we're uncovering clues about the hidden forces shaping the universe, and as long as they linger in the shadows, they'll keep us questioning what we think we know. Now let's dig deeper into the resilience of these ghostly giants. How do ultra-diffuse galaxies, or UDG, manage to hold themselves together in the chaotic whirlwind of the COMA cluster? It's like watching a delicate spiderweb withstand a hurricane. Seemingly impossible, yet somehow they do. The key lies in the brutal gravitational forces at play. In a cluster as crowded as COMA, galaxies are constantly tugged and twisted by their neighbors, a process known as tidal stripping. Normally, this would shred a faint, loosely bound galaxy to pieces. But UDGs aren't just surviving, they're thriving, and that forces us to ask why. One compelling idea is that dark matter plays the role of an invisible anchor. Picture a ship in a storm held steady by a massive, unseen weight beneath it. If UDGs are embedded in dense halos of dark matter, that could explain their stability. The dark matter's gravity would act like cosmic glue, keeping the stars from being ripped away even as the cluster's tides pull at them. But here's where things get even stranger. Some UDGs don't seem to have much dark matter at all, yet they still endure. This throws a wrench into our understanding. If dark matter isn't the hero here, what is? Maybe these galaxies have an unusual structure, their stars spread out in a way that makes them less vulnerable to disruption. Or perhaps the cluster's tides work slower than we thought, giving UDGs time to adapt rather than shatter. Then there's the bigger picture. The survival of UDGs hints at how dark matter is spread through the cluster. If they're shielded by dark matter halos, that suggests it's clumped in unexpected ways. If they're not, it means our models of galaxy formation might be missing a crucial piece. Either way, these faint galaxies are forcing us to rethink the rules of cosmic survival. So while UDGs may look fragile, they're teaching us some of the toughest lessons about the universe. Their persistence in the face of chaos isn't just a curiosity. It's a clue, one that could unravel the hidden workings of dark matter itself. Now let's turn our attention to something even more enigmatic: the COMA cluster's colossal radio halo. Imagine a faint, crackling whisper of radio waves stretching across millions of light years, wrapping the entire cluster like an invisible shroud. This isn't just background noise, it's a cosmic mystery, one that defies easy explanation. Radio halos are rare, and the one surrounding the COMA cluster is among the most massive ever observed. It's made up of high-energy particles, likely electrons, zipping through space at nearly the speed of light. But here's the puzzle: where do these particles get their energy? Normally, you'd expect them to come from violent events, like supernova explosions or jets blasted out by supermassive black holes. Yet, in the COMA cluster, there's no obvious source pumping out enough power to sustain such a vast radio glow. One leading theory points to the cluster's turbulent past. The COMA cluster didn't form peacefully. It grew through violent collisions, with smaller galaxy groups smashing together over billions of years. These cosmic crashes could have sent shockwaves rippling through the cluster's gas, accelerating particles to extreme energies. Think of it like stirring a pot of water. The swirling motion creates eddies and currents, and in this case, those chaotic motions might be generating the radio halo. But there's a catch. While mergers could explain part of the story, they don't fully account for the halo's sheer size and uniformity. If shocks from collisions were the only source, we'd expect the radio emission to be patchy, concentrated near the sites of past crashes. Instead, the halo is smooth and spread evenly, almost as if something invisible, is keeping the particles energized across the entire cluster. That's where things get speculative. Some scientists suggest that turbulence in the cluster's magnetic fields could play a role, acting like a giant particle accelerator. Others wonder if dark matter interactions, though highly hypothetical, might contribute. Whatever the answer, the radio halo isn't just a curiosity. It's a window into the extreme physics at work in the universe's most crowded neighborhoods. So while we don't yet know what's powering this immense radio whisper, one thing is clear: the COMA cluster's halo is more than just static. It's a signal, a clue waiting to be decoded, and solving its riddle could reveal secrets about how the universe energizes its most hidden corners. Now let's dig deeper into the idea that the COMA cluster's radio halo might be tied to its violent history of galactic collisions. Picture this: billions of years ago, smaller groups of galaxies, each with their own gravity and motion, slammed into one another, merging to form the colossal cluster we see today. These cosmic pile-ups weren't gentle. They sent shockwaves ripping through the cluster's gas like tidal waves in an ocean of superheated plasma. Those shocks could have acted like natural particle accelerators, boosting electrons to nearly the speed of light. When these high-energy particles spiral around magnetic fields, they emit the radio waves we detect as the halo. It's a compelling explanation, especially since we've seen similar, though smaller, radio emissions in other merging clusters. But here's where the theory starts to unravel. If mergers were the sole cause, the radio halo should look uneven brighter in regions where collisions were most violent, fainter where things were quieter. Instead, the glow is remarkably smooth, stretching uniformly across the entire cluster. It's as if something else is spreading energy evenly, like a cosmic mixer keeping the particles stirred up long after the initial crashes. One possibility is that turbulence, leftover chaos from those ancient mergers, continues to churn the cluster's gas, keeping electrons energized. Another idea involves the cluster's magnetic fields, which might trap and re-accelerate particles over vast distances. But even these explanations fall short of accounting for the halo's sheer scale. That's why some researchers are looking beyond conventional physics. Could dark matter, which makes up most of the cluster's mass, play a hidden role? It's a long shot, but if dark matter particles occasionally collide and annihilate, they might release energy that helps sustain the halo. For now, though, that remains speculative. What's clear is that the COMA cluster's radio halo isn't just a relic of past violence, it's an ongoing puzzle. The mergers set the stage, but the full story requires something more, something we haven't quite figured out yet. And that's what makes this phenomenon so fascinating. It's not just about what happened billions of years ago, but what's still happening out there in the depths of space. Now, shifting our gaze to another cosmic oddity, let's talk about the strange motion of galaxies within the COMA cluster. If you thought galaxies in a cluster would move in predictable, orderly ways, think again. Observations reveal that many of these galaxies are zipping around at speeds that shouldn't be possible based on the visible matter alone. It's as if the cluster's gravity is far stronger than what we can account for with stars, gas, and dust. So, what's going on? One leading idea points to hidden mass, likely dark matter lurking in the cluster, exerting an invisible gravitational pull. If dark matter is unevenly distributed, it could explain why some galaxies are moving faster than expected, like invisible hands tugging them along. But here's the twist: even when we factor in dark matter, some galaxies still don't move as predicted. Their trajectories are off, leaving scientists scratching their heads. That's where alternative theories come in. Some researchers suggest that our understanding of gravity itself might need an update. Modified gravity theories, like MND, short for modified Newtonian dynamics, propose that gravity behaves differently on cosmic scales than what Newton or Einstein predicted. In this view, the strange motions might not require dark matter at all, just a tweak to the laws of physics. But before we rewrite the textbooks, there's a catch. While MND can explain some odd motions, it struggles with other observations, like the way galaxy clusters bend light through gravitational lensing. So, for now, the mystery remains unsolved. Are we missing invisible matter, or is gravity itself playing by different rules? The COMA cluster isn't giving up its secrets easily, but that's what makes it such a thrilling puzzle. And speaking of puzzles, this isn't the only enigma the cluster has in store. Up next, we'll explore how the hot gas between galaxies might be stirring the pot, adding yet another layer to this cosmic conundrum. Now, let's turn our attention to the fiery sea of gas swirling between the galaxies of the COMA cluster. This isn't just any ordinary gas, it's a scorching million-degree plasma that fills the vast spaces between galaxies, and it might hold clues to the strange motions we've been seeing. You'd think something as thin as gas wouldn't have much sway over massive galaxies, but in the COMA cluster, it's a different story. This intracluster gas is so hot and energetic that it creates a dynamic environment, almost like a cosmic wind pushing and pulling on galaxies as they move. Some researchers believe this gas could be giving certain galaxies an extra kick, speeding them up beyond what gravity alone would predict. But here's where things get tricky. While the gas can explain some of the odd movements, it doesn't account for all of them. For one, the gas isn't evenly spread. It's clumpy and turbulent, with pockets of higher density that could influence nearby galaxies more than others. Yet, even when we map out these variations, some galaxies still move in ways that defy expectations. It's as if the gas is only part of the puzzle, leaving gaps in our understanding. Another complication: the gas itself is influenced by the very galaxies it's supposed to be affecting. As galaxies plow through this hot plasma, they can stir it up, creating shock waves and turbulence that ripple through the cluster. This feedback loop makes it even harder to pin down exactly how much the gas is shaping galaxy motions versus other forces at play. So, where does that leave us? Current models try to balance the gravitational pull of dark matter, the push and pull of intracluster gas, and even the possibility of modified gravity. But none of them fully explain every twist and turn in the COMA cluster's galactic dance. It's a reminder that the universe loves to keep us guessing, and the more we learn, the more questions arise. And just when you think the mysteries can't get any deeper, the COMA cluster has another surprise in store. Up next, we'll uncover why this cosmic neighborhood has an overabundance of dwarf galaxies, and what that tells us about the hidden workings of the universe. Now let's zoom in on one of the COMA cluster's most puzzling quirks, its surprising abundance of dwarf galaxies. These tiny cosmic neighbors, far smaller than giants like the Milky Way, are scattered throughout the cluster in numbers that defy expectations. You might assume that in a crowded, chaotic place like the COMA cluster, these delicate dwarfs would be rare, swallowed up by larger galaxies or torn apart by gravitational forces. Yet they're everywhere. Scientists estimate there could be thousands of them, far more than predicted by simulations of galaxy formation. This overabundance isn't just a curiosity, it's a direct challenge to our understanding of how galaxies evolve in dense environments. So, why does this mismatch exist? One leading idea is that many of these dwarfs are ancient survivors, relics from the early universe that somehow avoided destruction. Another possibility is that the cluster's extreme environment actually fosters their creation, with turbulence and collisions sparking the birth of new small galaxies. But neither theory fully explains why there are so many or why they're distributed the way they are. Here's where it gets even more intriguing. Dwarf galaxies are often packed with dark matter, which should make them resilient. Yet in the COMA cluster, some appear to be missing this invisible scaffolding entirely, leaving them oddly fragile. Others seem to cluster together in ways that suggest they're bound by unseen forces, hinting at structures we don't yet understand. This overabundance isn't just a local mystery, it ties into a bigger cosmic puzzle known as the missing satellite problem. Simulations of the universe predict even more dwarf galaxies than we observe, yet in places like the COMA cluster we see the opposite. It's as if the rules change in these dense environments, leaving astronomers scrambling to rewrite the playbook. What's clear is that these tiny galaxies hold big secrets. Whether they're survivors, newcomers, or something entirely unexpected, their presence forces us to rethink how galaxies live, die, and thrive in the universe's most extreme neighborhoods. And speaking of cosmic rule breakers, our next mystery takes us even deeper into the unknown, where supermassive black holes defy expectations in ways no one saw coming. But here's the twist: the COMA cluster isn't just an outlier. It's spotlighting a cosmic contradiction that has baffled scientists for decades. Across the universe, simulations of dark matter and galaxy formation predict a sea of dwarf galaxies orbiting larger ones like moons around a planet. Yet when we look up, we find far fewer than expected. This gap between theory and observation is known as the missing satellite problem, and the COMA cluster is turning it on its head. Instead of too few dwarfs, we're seeing too many, especially in this dense galactic metropolis. It's as if the cluster flipped the script, creating a mirror version of the puzzle. Normally, the missing satellite problem suggests something is suppressing dwarf galaxy formation or making them too faint to detect. But in the COMA cluster, the opposite seems true. The environment here might be preserving or even manufacturing these tiny galaxies in ways we don't yet grasp. One clue lies in dark matter. Most simulations assume dwarf galaxies are anchored by hefty halos of this invisible substance, which should make them stable and long-lived. Yet in the COMA cluster, some dwarfs appear to lack this dark matter shield, while others are clumped together in ways that hint at unseen forces at work. Could the cluster's extreme gravity be stripping dark matter away, or rearranging it into strange new configurations? Or is there another, even weirder mechanism in play? What makes this especially puzzling is that the COMA cluster's dwarf galaxies don't just defy expectations, they challenge the very tools we use to model the cosmos. If our simulations can't explain why some regions have too few dwarfs while others have too many, it suggests we're missing a critical piece of the galactic puzzle. Perhaps dark matter behaves differently in crowded environments, or maybe the cluster's violent history filled with collisions and mergers has rewritten the rules entirely. Whatever the answer, one thing is certain: the COMA cluster isn't just a backdrop for these mysteries. It's an active participant, warping our understanding of galaxy evolution in real time. And as we peel back the layers, we're forced to ask, are the missing satellites really missing? Or have they been hiding in plain sight, waiting for us to rethink where and how we search for them? Now, let's turn to another enigma lurking in this cosmic crowd, where the supermassive black holes at the hearts of galaxies aren't playing by the rules either. But just when we think the COMA cluster can't get any stranger, it throws another curveball our way, this time involving the cosmic heavyweights lurking at the centers of galaxies. Supermassive black holes are supposed to be a universal constant, with nearly every large galaxy hosting one in its core. Yet here, in this crowded galactic neighborhood, something doesn't add up. Astronomers expect to find hundreds of these gravitational monsters scattered across the cluster, given its sheer number of galaxies, but observations reveal far fewer than predicted. It's as if the COMA cluster has a black hole shortage, or worse, that we're missing them entirely. This discrepancy raises a glaring question: where are all the supermassive black holes hiding? One possibility is that many of them are dormant, lying silent after exhausting their surrounding fuel. Unlike their active counterparts, which light up as they devour gas and dust, dormant black holes are far harder to detect. In a cluster as chaotic as this, with galaxies constantly jostling and gas being stripped away, it's plausible that many black holes have simply gone dark. But there's another, more intriguing explanation. Some black holes might have been ejected entirely, kicked out of their host galaxies during violent mergers. When two galaxies collide, their central black holes can spiral toward each other, eventually merging in a cataclysmic event. The resulting gravitational waves could launch the newly formed black hole outward at incredible speeds, sending it hurtling into the void between galaxies. If this happens often in the COMA cluster, it could explain why we're not spotting them where we expect. Then there's the puzzle of size. Some of the black holes we do detect seem oddly small for the galaxies they inhabit, suggesting they might be growing slower or differently than models predict. Could the cluster's extreme environment be stifling their growth? Or are we seeing the remnants of black holes that were stripped of their feeding material long ago? Whatever the reason, this black hole discrepancy forces us to rethink how these cosmic giants form and evolve in dense environments. The COMA cluster isn't just hiding its dwarfs and dark matter. It's playing games with the most powerful objects in the universe. And as we dig deeper, we're left wondering, are the missing black holes truly absent, or are we just not looking the right way? Now, let's shift our gaze to another oddity in this cosmic menagerie. Objects so dense and strange, they blur the line between galaxies and star clusters. But the mystery of the missing black holes doesn't end there. If they're not ejected or dormant, could they simply be hiding in plain sight? The dense, chaotic environment of the COMA cluster makes detecting black holes, especially quiet ones, a monumental challenge. Imagine trying to spot a shadow in a room already dimly lit. That's what astronomers face when searching for black holes here. In a cluster packed with galaxies, gas, and dust, the usual telltale signs like X-ray emissions from hot, swirling material can get drowned out by the cosmic noise. Even if a black hole is actively feeding, the surrounding chaos might mask its presence, leaving it virtually invisible to our telescopes. Then there's the issue of orientation. Some supermassive black holes might be obscured by thick rings of dust and gas, their accretion disks tilted edge-on from our perspective. In these cases, the very material that should make them visible instead acts like a cosmic blindfold, blocking our view entirely. It's like trying to peer through a dense fog. We know something's there, but the details are frustratingly out of reach. Even gravitational lensing, a powerful tool for spotting hidden mass, struggles in the COMA cluster's crowded core. The sheer number of overlapping galaxies and dark matter structures creates a tangled web of distortions, making it nearly impossible to isolate the subtle tug of a single black hole. So, are these black holes truly missing, or are we just missing them? the answer might lie in the next generation of telescopes, equipped with sharper vision and better tools to cut through the cosmic clutter. Until then, the COMA cluster keeps its secrets close, reminding us that even the most powerful objects in the universe can vanish when the conditions are just right. Now let's turn to another enigma object so bizarre, they defy even our basic definitions of what a galaxy should be. But the COMA cluster's surprises don't stop there. Nestled among its countless galaxies are objects so strange, they challenge everything we think we know about cosmic structures. Meet ultra-compact dwarfs, or octa-tiny, enigmatic worlds that pack more stars than some full-sized galaxies into a space no larger than a globular cluster. Picture a city squeezed into a single building. That's the density of a UCD. These objects are so crammed with stars, they outshine entire dwarf galaxies despite being a fraction of the size. But here's the puzzle. Are they the stripped-down cores of once larger galaxies or something else entirely? The debate hinges on their bizarre properties. UCDs weigh in at millions of times the mass of our Sun, far heavier than any known star cluster. Some even harbor supermassive black holes at their centers, a feature typical of galaxies, not clusters. This has led astronomers to wonder, could these be the skeletal remains of galaxies torn apart by the COMA cluster's brutal gravity, leaving only their dense hearts behind? Yet others argue UCDs might be super-sized star clusters born from cosmic collisions. When galaxies merge, the chaos can trigger the formation of incredibly dense stellar nurseries. Over time, these could evolve into the UCDs we see today. But if that's true, why do so many of them act like miniature galaxies, complete with dark matter halos and ancient stars? The COMA cluster's UCDs refuse to fit neatly into either category, blurring the line between galaxy and cluster. And with each new discovery, they force us to rethink how cosmic structures form and evolve. One thing's certain, in a universe full of mysteries, these tiny titans stand out as some of the most perplexing. Now, let's dig deeper into the two leading theories battling to explain their origins and why neither quite solves the puzzle. So where does the evidence point in this cosmic tug of war between theories? Let's start with the stripped galaxy hypothesis. If ultra-compact dwarfs are the surviving cores of larger galaxies, we'd expect them to share key traits with their galactic ancestors, and some do. A handful of UCDs in the COMA cluster have been caught red-handed with features you'd never find in a star cluster: faint outer shells of stars, debris trails, and even dark matter halos. These are telltale signs of a galaxy being ripped apart, leaving only its dense central bulge behind. Then there's the black hole connection. Remember how some UCDs pack supermassive black holes at their centers? That's a galactic signature. Star clusters, no matter how massive, don't form black holes of that scale. It's like finding a skyscraper's foundation under what you thought was a backyard shed. Something much bigger must have come first. But the star cluster theory fights back with its own compelling evidence. Many UCDs lack those galactic fingerprints entirely. No dark matter, no debris shells, just a smooth, dense ball of stars chemically identical to globular clusters, only larger. Supporters argue these could be the result of extreme star formation during galaxy collisions. When two galaxies merge, the shockwaves can compress gas into superstar clusters, so dense they rival small galaxies in mass. Over billions of years, these could mature into the UCDs we see today. Here's where things get messy. The COMA cluster's UCDs don't neatly split into two camps. Some show mixed traits, like having a black hole but no dark matter, or ancient stars arranged in ways that defy both theories. It's as if the universe took both explanations, scrambled them together, and added new mysteries we haven't even identified yet. What's clear is that ultra-compact dwarfs are rewriting the rules. Whether they're galactic survivors, stellar overachievers, or something entirely new, each discovery peels back another layer of this cosmic enigma. And with the COMA cluster hosting so many of these oddballs, it remains ground zero for cracking their secrets. Now, let's turn to another head-scratcher in this cluster: why so many of its galaxies have mysteriously stopped making new stars. Shifting our gaze to another cosmic puzzle, we arrive at a silent graveyard of star formation within the COMA cluster. Here, countless galaxies sit frozen in time, their gas reservoirs intact but eerily inactive. Unlike vibrant spiral galaxies like our Milky Way, bursting with newborn stars, these cosmic islands have entered a dormant phase, and scientists are piecing together why. The culprit: the cluster's own extreme environment. Imagine a galaxy as a chef trying to cook new stars with gas as its ingredients. Now drop that chef into a hurricane. That's life for galaxies in the COMA cluster, where three brutal forces conspire to snuff out star birth. First, there's ram pressure stripping a cosmic wind of superheated gas between galaxies that acts like a sandblaster, tearing away star-forming fuel. Observations show long, ghostly tails of gas streaming behind these galaxies, evidence of this violent theft in progress. Then comes gravitational harassment. In this crowded metropolis of galaxies, close encounters warp shapes and disrupt gas clouds before they can collapse into stars. Picture trying to light a candle in a room where strangers keep bumping into you. It's nearly impossible. Finally, the cluster's intense heat plays a role. Without cool gas, stars can't form, and the COMA cluster's intracluster medium reaches temperatures of millions of degrees, effectively pressure cooking any potential stellar nurseries. Yet the mystery deepens when we spot exceptions. A rare few galaxies, like the spiral NGC 4921 we'll discuss later, still cling to star formation against all odds. Their survival hints at unknown protective mechanisms, perhaps dense gas cores shielded from stripping, or orbits that avoid the cluster's most violent regions. What makes this phenomenon so crucial is its cosmic timing. The COMA cluster serves as a preview of our universe's future, where galaxy clusters will increasingly dominate. By decoding why star formation dies here, we're reading the fate of most galaxies billions of years from now. Next, we'll examine the specific process of ram pressure stripping that makes the COMA cluster such an efficient star formation killer. Now let's take a closer look at one of the most dramatic forces at work in the COMA cluster: ram pressure stripping. This process is like a cosmic tug of war, where the superheated gas between galaxies acts as an invisible hand, yanking away the raw materials needed for new stars. Picture a galaxy moving through the cluster at high speed, like a car driving through a heavy rainstorm. The intracluster gas, so thin it's practically a vacuum by Earth standards, still packs enough punch to peel away a galaxy's loosely held hydrogen clouds. These are the same clouds that would normally collapse under gravity to form stars, but in the COMA cluster, they're often ripped away, leaving behind trails that glow faintly in X-rays. What's fascinating is how differently galaxies respond to this assault. Some, especially smaller or gas-rich spirals, get completely gutted, transforming into jellyfish galaxies with long, shimmering tails of stolen material. Others, particularly those with dense central bulges, manage to hold onto their star-forming fuel. It's like comparing a sturdy oak tree weathering a storm versus a sapling getting uprooted. The deeper the gravitational roots, the better the survival chances. Recent observations reveal another twist: galaxies on their first plunge into the cluster suffer the worst stripping, while those orbiting the outskirts experience it more gradually. There's even evidence that some galaxies might briefly reignite star formation as stripped gas gets compressed at their edges, creating a final burst of stellar birth before the fuel runs out completely. The real mystery lies in the outliers, those rare galaxies that somehow keep forming stars despite being deep in the cluster's danger zone. Some may have entered the cluster with unusually large gas reserves, buying them extra time. Others might be on orbits that avoid the densest, most hostile regions of intracluster gas. There's even speculation that magnetic fields could act like protective shields around certain galaxies, though this remains unproven. Understanding these survivors could rewrite parts of galactic evolution theory, showing that star formation doesn't always end quietly, sometimes it goes down fighting. Next, we'll turn our attention to the eerie glow of stars floating freely between galaxies, a ghostly relic of the cluster's violent past. Now, let's shift our gaze to something hauntingly beautiful, the faint, ghostly glow known as intracluster light. This eerie illumination doesn't belong to any single galaxy, but instead comes from countless stars adrift in the vast emptiness between them, like cosmic fireflies lost in the dark. These wandering stars didn't start their lives untethered. They were once part of galaxies, but the COMA cluster's violent history, galactic collisions, near misses, and brutal tidal forces ripped them loose. Picture two galaxies passing too close, their gravitational pull stretching and shredding each other, scattering stars into the void like sparks from a grindstone. Over billions of years, these orphaned stars accumulated, creating a faint but detectable glow that permeates the entire cluster. What makes this light so revealing is its distribution. It's not uniform. Instead, it traces the cluster's most chaotic regions, highlighting where the fiercest interactions occurred. In some areas, the glow forms delicate streams like ribbons of stardust, marking the paths of ancient galactic encounters. Elsewhere, it pools into diffuse clouds, evidence of galaxies torn apart so completely that only their stars remain. Astronomers can even use this light to estimate the cluster's age and past violence. The more intracluster light there is, the more collisions and mergers the cluster has endured. In the COMA cluster, the sheer abundance of this glow suggests a history of near-constant upheaval, with galaxies smashing together or stripping each other bare over eons. But here's the twist: some of these stars might not be true orphans. A few could belong to ultra-faint dwarf galaxies, too dim to detect individually, while others might have been born right in the intracluster space from gas stripped during collisions. It's a reminder that even in the harshest environments, the universe finds ways to create and adapt. This ghostly light isn't just a relic, it's a living archive telling the story of how galaxies evolve, collide, and sometimes fade into the darkness. Up next, we'll examine the uneven and mysterious X-ray emissions that add another layer of intrigue to the COMA cluster's already puzzling profile. Now, let's take this ghostly glow a step further and uncover what it reveals about the COMA cluster's turbulent past. The distribution of intracluster light isn't random, it's a cosmic breadcrumb trail, pointing directly to the cluster's most dramatic collisions and mergers. Think of it as a forensic tool for astronomers, allowing them to reconstruct ancient galactic smash-ups with surprising precision. Where the light forms long, delicate streams, it often marks the paths of galaxies that once grazed each other, their stars pulled out like taffy by gravitational forces. These streams act like celestial chalk outlines, tracing the trajectories of close encounters that happened billions of years ago. In denser regions where the glow pools into broad clouds, it signals something far more violent. Full-blown mergers where galaxies were torn apart completely, their stars scattered like confetti. By studying these patterns, scientists can even estimate the timing of these collisions. Younger streams appear sharper and more defined, while older ones have blurred and faded, their stars gradually mixing into the general haze of the cluster. It's like reading tree rings. Each layer of light tells a story of when and how galaxies interacted. But here's where it gets even more fascinating. Some of these stellar trails don't match any known galaxies in the cluster today. That means they could be the last remnants of galaxies that were utterly destroyed, their stars all that's left to prove they ever existed. Other faint arcs might hint at smaller, unseen galaxies still lurking in the darkness, waiting to be discovered. This intracluster light isn't just a static relic. It's a dynamic record, constantly updated as new collisions unfold. every galactic encounter leaves its mark, adding another layer to this luminous archive. And as astronomers refine their tools, they're uncovering even finer details, like stellar populations with different ages or compositions, revealing not just where galaxies collided, but how they evolved before their final demise. So next time you picture the COMA cluster, imagine it not just as a collection of galaxies, but as a vast crime scene with intracluster light illuminating the evidence of its most epic cosmic brawls. Up ahead, we'll turn our attention to another enigma, the uneven and puzzling X-ray emissions that add yet another twist to this cluster's mysteries. But the mysteries of the COMA cluster don't stop with its ghostly stellar glow. Shifting our gaze to another cosmic puzzle, we encounter something even more perplexing: the cluster's strange and uneven X-ray emissions. Unlike the visible light from stars or the radio waves we've discussed earlier, these high-energy X-rays paint a picture that defies simple explanation. What makes these emissions so baffling? For starters, they don't neatly match up with the cluster's galaxies or the vast clouds of hot gas we'd expect to be their source. Instead, they appear in patches, some blazing intensely, others faint or absent entirely, creating a splotchy, unpredictable pattern across the cluster. It's as if someone flicked a cosmic flashlight on and off at random, leaving astronomers scratching their heads. One leading theory points to active galactic nuclei, or supermassive black holes at the centers of galaxies that devour surrounding material, spewing out X-rays in the process. But here's the catch: many of these X-ray hotspots don't line up with known AGN. That raises the tantalizing possibility that some black holes might be hidden, either buried under thick dust or sitting quietly without the telltale signs of feeding. Then there's the dark matter angle. While dark matter itself doesn't emit light, some theories suggest it could interact in ways that produce X-rays, perhaps through collisions of hypothetical particles. If true, these emissions might offer our first indirect glimpse of dark matter's hidden behavior. But so far, the evidence is circumstantial at best, leaving this idea in the realm of speculation. Adding to the intrigue, the X-rays also reveal pockets of gas that are far hotter or cooler than their surroundings, as if the cluster's atmosphere has been stirred by some unseen force. Turbulence from past collisions or energy injected by AGN could explain some of this, but not all. The inconsistencies suggest there's still a missing piece to this puzzle, one that might rewrite how we understand the interplay between galaxies, gas, and the invisible scaffolding of dark matter. As we peel back the layers of this X-ray enigma, one thing becomes clear: the COMA cluster refuses to play by the rules, and just when we think we've got a handle on its secrets, it throws another curveball our way. Next up, we'll dig into whether these bizarre emissions could be tied to one of the universe's most elusive phenomena: fast radio bursts. Now, let's take a closer look at the two most compelling explanations for these erratic X-ray emissions: hidden active galactic nuclei and the elusive influence of dark matter. Both possibilities push the boundaries of what we know about cosmic energy and the invisible forces shaping the universe. Active galactic nuclei, or AN, are powerhouses of radiation, fueled by supermassive black holes guzzling down surrounding matter. Normally, they're easy to spot because of their bright, energetic outbursts, but in the COMA cluster, some X-ray sources don't seem to match up with any visible AGN. This raises a fascinating question. Could there be black holes lurking in the shadows, either obscured by thick clouds of dust or sitting idle in a quiet phase? If so, their faint X-ray signatures might be the only clue to their existence, forcing astronomers to rethink how they track these cosmic monsters. Then there's the dark matter hypothesis, an idea that's as thrilling as it is controversial. Dark matter doesn't emit light, but some theories suggest certain types of dark matter particles could collide and annihilate each other, releasing X-rays in the process. If true, these emissions might be our first real evidence of dark matter's hidden behavior. However, proving this is a monumental challenge. the signals are faint, and other explanations like hidden AGN or turbulent gas can't be ruled out yet. Still, the possibility lingers, teasing us with the chance to finally crack one of astrophysics' greatest mysteries. What makes this debate so intriguing is that both explanations, hidden AGN and dark matter interactions, would fundamentally change our understanding of the COMA cluster. Either we're missing a population of stealthy black holes, or we're glimpsing the fingerprints of an invisible cosmic ingredient. Until we gather more data, the truth remains just out of reach, leaving us to wonder, is the answer hiding in plain sight, or is it something far stranger than we've ever imagined? As we move forward, keep this puzzle in mind, because the next phenomenon we'll explore, fast radio bursts, might just hold a surprising connection to these very X-ray mysteries. Now, shifting our gaze to another cosmic puzzle, let's talk about fast radio bursts, those fleeting, high-energy signals that have baffled astronomers since their discovery. Reports have surfaced of FRBs originating near the COMA cluster, sparking intense debate about whether this extreme environment could be their source. These bursts last just milliseconds, but they pack more energy than the Sun emits in days. The fact that some seem to come from the vicinity of the COMA cluster raises a tantalizing question. Is there something about this dense, turbulent region that's triggering them? One leading theory points to magnetars, highly magnetized neutron stars that occasionally unleash violent flares. The COMA cluster's crowded, chaotic environment could be the perfect breeding ground for these cosmic powerhouses, with their intense magnetic fields potentially generating FRBs. But here's the catch: while magnetars are a strong candidate, no one has yet pinned an FRB definitively to one in the COMA cluster. The bursts are so brief and unpredictable that tracing them back to a specific object is like trying to catch a lightning bolt in a bottle. Then there's the wildcard possibility. Could FRBs be tied to the very X-ray mysteries we just explored? Some researchers speculate that interactions between dark matter or hidden black holes might produce these bursts, though evidence is thin. It's a long shot, but the idea underscores how much we still don't understand about the forces at play in the COMA cluster. What makes this enigma so gripping is the sheer range of explanations, from known objects like magnetars to exotic, uncharted physics. Each detected FRB near the cluster adds another piece to the puzzle, yet the full picture remains frustratingly out of focus. For now, these bursts serve as a reminder that the COMA cluster isn't just a collection of galaxies, it's a cosmic laboratory, pushing us to rethink what's possible in the universe. And as we peel back another layer of mystery, our next stop takes us deeper into the cluster's fiery heart, where the gas between galaxies burns hotter than anyone expected. Now let's dig deeper into the magnetar debate, because while these cosmic powerhouses are strong contenders, they're not the only game in town. Magnetars, with their unimaginably strong magnetic fields, can indeed produce bursts of energy that match the intensity of fast radio bursts. Picture a neutron star so magnetized it could strip the data off every credit card on Earth from halfway across the galaxy. When these objects undergo starquakes or magnetic reconnection, they unleash flares that could, in theory, explain FRBs. The COMA cluster's dense environment, packed with galaxies and stellar remnants, seems like the perfect place to find such extreme objects, yet there's a hitch. While magnetars check many boxes, no one has ever caught one in the act of producing an FRB within the cluster. The bursts are so fleeting and the cluster so crowded that linking them directly to a magnetar feels like finding a needle in a cosmic haystack. Some scientists argue that if magnetars were the sole source, we'd see more predictable patterns or afterglows, clues that just haven't materialized. This opens the door to wilder possibilities. Could FRBs stem from something even more exotic? One fringe theory suggests collisions between dense objects like neutron stars and black holes might generate these bursts. Others speculate about cosmic strings, hypothetical defects in spacetime, or even advanced alien technology, though that's firmly in the realm of speculation. The most intriguing angle ties back to the cluster's other mysteries. What if FRBs are a side effect of the same unknown processes heating the intracluster gas or powering those unexplained X-ray emissions? The truth is, the Magnetar explanation fits neatly, but neat doesn't always mean correct in astronomy. The COMA cluster keeps throwing curveballs, forcing us to consider that FRBs might be a symptom of something we haven't even imagined yet. Every burst detected near the cluster is a breadcrumb, but the trail leads deeper into the unknown. And speaking of heat, our next mystery takes us to the cluster's scorching core, where the gas between galaxies is hotter than standard physics can explain. Now, let's turn up the heat literally, because the gas floating between galaxies in the COMA cluster isn't just hot, it's unreasonably hot. Imagine a cosmic sauna where temperatures soar to tens of millions of degrees, far beyond what typical astrophysical processes should produce. This isn't just a quirk, it's a full-blown mystery that challenges our understanding of how galaxy clusters evolve. The intracluster gas, a thin but scorching plasma filling the space between galaxies, should theoretically cool over time as it radiates energy away. But in the COMA cluster, that's not happening. Instead, the gas stays blisteringly hot, defying expectations. Traditional heating mechanisms like supernova explosions or the gravitational energy released during galaxy mergers simply can't account for the sheer intensity of this heat. It's like tossing a few logs into a bonfire and somehow getting the temperature of the sun. One leading theory points to the cluster's supermassive black holes. As these monsters devour matter, they spew out jets of high-energy particles that could reheat the gas like a cosmic microwave on overdrive. But even this explanation falls short. The energy required to maintain the gas at these temperatures is staggering, and not all galaxies in the cluster host active black holes powerful enough to do the job. Another puzzle is the gas's uneven temperature distribution. Some regions are hotter than others, with no clear pattern tied to visible structures like galaxies or shock waves from collisions. This patchiness suggests hidden forces at work, perhaps turbulence stirred up by unseen dark matter interactions, or even residual energy from ancient cosmic events we've yet to uncover. The COMA cluster's overheated gas isn't just a local oddity, it's a window into the broader question of how energy moves through the universe's largest structures. And as we'll see next, the role of turbulence and magnetic fields in this cosmic furnace only deepens the intrigue. Now, let's stir things up, because the COMA cluster's overheated gas isn't just sitting still. Turbulence, the chaotic churning of matter, could be playing a major role in keeping temperatures sky-high. Picture a pot of water boiling violently with currents swirling in all directions. On a cosmic scale, that's what might be happening here. As galaxies move through the cluster, they drag and twist the intracluster gas, creating whirlpools of energy that prevent it from cooling down. But here's the catch: modeling this turbulence is incredibly tricky. The sheer scale of these motions, spanning millions of light-years, makes it hard to simulate accurately, even with our most advanced supercomputers. Then there's the invisible hand of magnetic fields. These cosmic force lines, woven through the gas like an intricate web, could be trapping heat and preventing it from escaping. Think of them as insulation wrapped around the cluster, keeping the energy locked in. Some theories suggest these fields might even amplify turbulence, creating a feedback loop that cranks up the temperature even further. But proving this is another challenge. Magnetic fields are notoriously difficult to detect in the vast emptiness of space, and their strength and structure in the COMA cluster remain poorly understood. What's fascinating is how these two factors, turbulence and magnetic fields, might interact. Could they work together to sustain the gas's extreme heat, or does one dominate the other? Right now, astronomers are piecing together clues from faint radio emissions and X-ray patterns, but the full picture is still hazy. And until we crack this cosmic puzzle, the COMA cluster's scorching gas will remain one of space's most stubborn mysteries. Up next, we'll shift our gaze to a rare rebel in this fiery environment, a spiral galaxy that somehow thrives where others fade. Now, let's turn our attention to a true cosmic oddball, NGC 4921. In a cluster dominated by old, red, and lifeless elliptical galaxies, this spiral stands out like a vibrant splash of color in a grayscale world. Unlike its neighbors, which have long since stopped forming stars, NGC 4921 is still actively birthing new ones, defying the harsh conditions of the COMA cluster. What makes this galaxy so special? For starters, its delicate spiral arms are a rarity in such a crowded, violent environment. Most spirals that wander into the cluster get their gas stripped away by the intense gravitational forces and scorching intracluster medium, leaving them starved and stagnant. But NGC 4921 has somehow held onto its star-forming fuel, resisting the fate that befell so many others. Astronomers suspect its survival might come down to timing and trajectory. Perhaps it arrived in the cluster more recently, or maybe it's moving on a path that spared it the worst of the gas-stripping effects. Another theory suggests it could be unusually rich in dark matter, whose gravitational grip helps shield its star-forming material from being torn away. Then there's its striking appearance, with its bright blue knots of young stars and faint, dusty arms. NGC 4921 offers a glimpse into what many galaxies might have looked like before the cluster's environment took its toll. It's like a cosmic time capsule, preserving a phase of galactic life that's been erased almost everywhere else in the COMA cluster. But the mystery deepens when we ask why it's alone. If conditions exist for one spiral to thrive, why aren't there more? This solitary rebel challenges our understanding of how galaxies evolve in extreme environments, and whether NGC 4921 is a lucky survivor or a sign that we're missing something fundamental about cluster dynamics. Up next, we'll dig into whether this galaxy is a relic from an earlier era, or if it's found a way to cheat the cluster's star-forming shutdown. So, is NGC 4921 a rare survivor from a bygone era? Or has it simply found a way to outsmart the COMA cluster's star-forming shutdown? Let's weigh the possibilities. One compelling argument is that this galaxy might be a relic, a holdover from a time when spirals were more common in the cluster. Billions of years ago, before the COMA cluster grew so dense and violent, galaxies like this could have thrived. Over time, most were stripped of their gas and transformed into featureless ellipticals. But NGC 4921 could be one of the last remnants of that earlier, more dynamic period, clinging to its spiral structure against all odds. On the other hand, maybe it's not about age at all. Perhaps this galaxy has unique properties that let it resist the cluster's destructive forces. Some studies suggest it might have an unusually strong magnetic field, which could act like a shield, protecting its gas from being ripped away. Others speculate that its orbit keeps it on the outskirts of the cluster, where the intracluster medium is less punishing. Then there's the dark matter angle. If NGC 4921 has a higher concentration of dark matter than its neighbors, that extra gravitational glue could help it hold onto its star-forming fuel longer. This would make it less of a relic and more of a cosmic outlier, defying the norm through sheer resilience. But here's the twist: if it's truly a survivor from an earlier epoch, why haven't we found more like it? The absence of similar spirals in the cluster raises doubts. Unless NGC 4921 is the lone holdout, which seems statistically unlikely. That's why some astronomers lean toward the idea that it's not ancient at all, but rather a galaxy that's found a clever way to endure in a hostile environment. Either way, this cosmic enigma forces us to rethink how galaxies interact with their surroundings. Whether it's a relic or a rebel, NGC 4921 proves that even in the most extreme places, nature finds a way to surprise us. Next up, we'll shift our gaze to the invisible threads that might weave the COMA cluster into the larger cosmic web, the dark matter filament hypothesis. Now, let's turn our attention to the invisible scaffolding of the cosmos, the dark matter filament hypothesis. Picture the universe not as a random scattering of galaxies, but as a vast, interconnected web. At the heart of this web are colossal threads of dark matter stretching across unimaginable distances, linking galaxy clusters like the COMA cluster to the rest of the cosmic structure. Scientists believe these filaments act as cosmic highways, guiding galaxies into clusters and shaping the large-scale architecture of the universe. But here's the catch: dark matter doesn't emit light or interact with electromagnetic forces, making these filaments nearly impossible to observe directly. So how do we even know they exist? The answer lies in their gravitational fingerprints. When light from distant galaxies passes near these filaments, their immense mass bends the light's path, a phenomenon known as weak gravitational lensing. By studying these subtle distortions, astronomers can map the otherwise invisible dark matter threads. In the case of the COMA cluster, these observations hint at sprawling filaments connecting it to neighboring clusters, like hidden bridges in the cosmic void. Another clue comes from the motion of galaxies themselves. Some galaxies on the outskirts of the COMA cluster appear to be flowing along predictable paths, as if being funneled by an unseen force. This aligns with simulations predicting that dark matter filaments should channel galaxies toward dense clusters, much like rivers merging into a lake. Yet, despite the mounting indirect evidence, definitive proof remains elusive. The filaments are so diffuse that even weak lensing struggles to pin them down with certainty. Some researchers argue that alternative explanations, like chance alignments of smaller dark matter clumps, could mimic filament-like signals. What's at stake here isn't just the existence of these filaments, but our entire understanding of how the universe organizes itself. If confirmed, they'd solidify dark matter's role as the cosmic architect, weaving clusters like COMA into the grand tapestry of the universe. Up next, we'll dig deeper into the tools astronomers use to hunt these filaments' gravitational lensing clues that might finally bring these ghostly structures into focus. Now, let's take a closer look at how astronomers are using gravitational lensing to hunt for these elusive dark matter filaments. Imagine space as a giant funhouse mirror. When light from distant galaxies passes through the gravitational field of a dark matter filament, it bends ever so slightly, distorting the shapes of those galaxies in predictable ways. This subtle warping, known as weak gravitational lensing, is like the universe's way of leaving fingerprints on the light that travels through it. By meticulously analyzing these distortions, scientists can reconstruct the invisible mass responsible for them. Think of it like mapping the outline of a shadow. You can't see the object casting it, but the shadow's shape gives you clues. In the COMA cluster, researchers have detected faint patterns in the light of background galaxies that suggest the presence of sprawling dark matter filaments, stretching far beyond the cluster's visible boundaries. But here's the challenge: these signals are incredibly subtle. The distortions are often smaller than the natural variations in galaxy shapes, making it like trying to spot a whisper in a thunderstorm. Even with advanced telescopes and painstaking data analysis, noise and cosmic imperfections can muddy the results. Some of the supposed filament detections might just be chance alignments of smaller dark matter clumps, or even quirks in the telescope's optics. Adding to the complexity, the filaments themselves are thought to be wispy and uneven, more like tangled spider silk than solid ropes. This means their lensing effects are patchy and hard to distinguish from random cosmic noise. To complicate things further, the COMA cluster's own chaotic environment, filled with galaxies, hot gas, and other structures, can mimic or mask the delicate signatures of filaments. Despite these hurdles, the hunt continues. New telescopes and techniques, like those measuring the polarization of light or combining data from multiple wavelengths, could sharpen our view. If we can finally pin down these filaments, it wouldn't just confirm their existence, it would reveal the hidden skeleton of the cosmos, showing us how dark matter stitches the universe together. Up next, we'll explore another mystery lurking in the COMA cluster, one that defies even our best cosmic models. Stay tuned. As we wrap up our journey through the COMA cluster's most baffling mysteries, one thing becomes undeniably clear. This cosmic neighborhood is a treasure trove of questions that defy our current understanding of the universe. From galaxies missing their dark matter to ghostly radio halos, from the strange motions of stars to the whispers of unseen filaments, each phenomenon we've explored peels back another layer of the cosmos's secrets, revealing just how much we still have to learn. The COMA cluster doesn't just challenge our theories, it forces us to rethink them. Whether it's the puzzling absence of black holes, the survival of fragile ultra-diffuse galaxies, or the scorching heat of intracluster gas, every anomaly pushes the boundaries of astrophysics. And while we've made incredible strides in mapping the universe, these mysteries remind us that some of the most fundamental pieces of the cosmic puzzle are still missing. So what's next? The hunt for answers continues, with new telescopes, sharper simulations, and bold ideas lighting the way. But here's the beautiful part: you don't have to be a scientist to join the adventure. The universe invites all of us to look up, wonder, and stay curious. If these mysteries sparked your imagination, hit that like button and let us know in the comments which phenomenon blew your mind the most. Don't forget to subscribe and ring the bell so you never miss our deep dives into the cosmos's greatest enigmas. After all, the universe still has countless stories left to tell, and we're just getting started. Keep exploring, stay amazed, and remember, the next big discovery could be just one observation